All right, so last time we started into the limit laws, and I think I just got through them, right? I through this page, but we didn't do anything on the next page. Is that correct, or do we still have something to go through on this one?
No, we got that.
Okay. So specifically, keep in mind that we had these two special cases. We said that the limit of a constant is just the constant. Okay? And the limit of the identity function is just the limiting value a. And I justified those to you with the graph, right? If here was the x value a, and we look at the limit as x approaches a of this constant function f of x equals c, it is just c. And you can see that because if this is the value c here, as my x values get closer and closer to c, as my x values get closer and closer to a, my y values are getting closer and closer to c. And in fact, I don't even have those arrows. It just, each time, it's just at that y value. Okay? Because here's the point being moved in closer and closer to when x equals a. Any questions on that? Okay. Likewise, if here's the limiting value a, because this is the identity function, keep in mind that this is the order pair a on the graph. And so what do we see as my x values get closer and closer to the domain value a? So let's keep track of domain and range, right? It's a little confusing in this example. As my x values are getting closer and closer to the domain value a, my y values are getting closer and closer to the range value a. So we would say the limit as x approaches a of this identity function is just a. So let's kind of keep in mind what we've just done. Okay. On the first page, we gave a bunch of properties of how to find new limits from old limits. And then I gave you two specific limits. Okay. We will prove these when we get to section 2.7 using the official way of proving a limit, which is pretty labor intensive. And at the end of the day, it's exactly what we said it should be. Okay. So we will prove it formally, but from here on, we're just going to take these two on faith. You can always take these two on faith. All right. So before I do property number 4, which is a useful one, we'll get to it in just a second here, I want to go ahead and actually work one of these problems. Okay. So we're going to evaluate the limit. We did not do this one, correct?
No.
Great. I'm going to evaluate this limit using my limit properties. Okay? Folks, it's going to be a lot of show, and then we're not going to be too excited with the result. Okay? The reason why is because this is a very well-behaved function here. There's nothing really exciting happening in this function. Okay? So when we go to take the limit, we're not really going to get any new information about it. Okay? But we're going to use our limit properties to get there. So it's going to be a lot of work for a little payoff. Okay? Later on, I'll give you a shortcut technique for a problem as simple as this one. Okay? And you'll probably see it right away. All right. So what am I doing here? Well, I'm taking the limit of this function. What does this function have in it? It has a bunch of sums and differences. What did we say about limits with respect to sums and differences? They distribute over, right? We said the limit of a sum was the sum of the limits. Okay? So that means I can rewrite this as the limit as x approaches a of 2x squared minus the limit as x approaches a of 3x plus the limit as x approaches a of 4. Everyone see what I did there? I distributed the limit over the sums and differences, which I'm allowed to do by that previous property. Okay? Which is one I think I will prove that property to you too. Okay, questions so far? So let's keep going. Notice here I've got a constant times the x squared function. Everyone see that? We're taking the limit of a constant times the x squared function. What did we say about constants? We said that constants factor out of limits. I'm not sure who said that. Oh, thank you, Angel. Yeah, we say that constants factor out of limits. Okay? So what can we do here? We can rewrite this as 2 times the limit as x approaches a of x squared minus, let's keep going with that idea, the limit, 3 times the limit as x approaches a of x. And what could I do with this last limit? Zara says this last limit is 4. Do you agree? Yeah. Because what are we taking the limit of? We're taking the limit of a constant. The limit of a constant is just that constant value as per the graph we just reviewed on the previous page. Okay? So this is equal to just, this expression right here simplifies to be just plus 4. Okay? We're getting close to being done. How am I going to deal with this x squared function? Any ideas on that? We can't take it. We can't introduce a square root that's not there. Okay. I will give you a property for how to deal with these squares in just a minute. But let's see if there's any properties on the previous page that would help us out. We had a sum property. We had a quotient property, we had a product property, we had a constants property. Of those, which one do you think we might be able to apply here?
Product.
A product. Can we think of x squared as a product?
Yeah. X times X.
It's x times x, right? Okay. So I'm going to take a line, it maybe a little bit too much writing, but we'll live. I'm going to take a line to rewrite this as a product just so you can see it. That's the limit as x approaches a of x times x. Minus 3. Let's go ahead and evaluate this one. What is the limit as x approaches a of the identity function? It's just a. It's just the limiting value, right? Okay. And again, we got that one from the graph on the previous page. So this is minus 3a plus 4. So let's be a little careful here. The limit stops. If I wanted to include all the rest of that in this current limit, I would have put parentheses all the way around the sum or difference, right? So now I've written x squared as a product, and what did we say about the product, or sorry, the limit of a product? Will? It's the product of the limits, right? So I can rewrite this as 2 times the limit as x approaches a of x times the limit as x approaches a of x minus 3a plus 4. Okay, does everyone see what I did there? Someone want to say what I just did? Summarize? Factored out isn't quite the word I'm looking for because it's not like a constant. It doesn't just come out of the limit.
So you distribute the limit?
Yeah, I distributed the limit over the product. Can I distribute limits over products? Yes. Okay. So we can rewrite this now as 2 times, what's the limit as x approaches a of x? It's a times a minus 3a plus 4. And here is that not very exciting result. Okay. Unfortunately, in a math class, if I do 2 completely different problems and get the same answer, students think I'm doing the same thing. Right? I did not plug a into this function. What did I do? I took the limit as x approaches a. Okay? Using these steps. So in some of your homework problems, you'll be asked to simplify this using limit properties, and you'll specify each step of the way which limit property you're using. Okay? I didn't just plug a in, right? What did we see in this case? In this case, we see that evaluating the limit as x approaches a gives me the same answer as if I had plugged in a, right? And we saw those examples before, right? So if I give you a graph right here, here's a, here's some value L. Okay? What is f of a? It's L. What is the limit as x approaches a of f of x?
It's L.
It's also L. Okay? But these are 2 separate ideas here, right? One is simply plugging a into the function. The second one is exploring the behavior as we approach a. Taking limits isn't too exciting for well-behaved functions. We don't really get any new information, okay? Which is why this result isn't too exciting to you. Okay? Let's go ahead and just summarize what we just did real quick. And I'm going to, on the next page, I want to give the direct substitution property. All right. This is going to be kind of a funny fill in the blank. Okay? So if f is a polynomial function or a rational function, and, it seems silly, but I'm emphasizing that, and what? A is in the domain of f. Okay? By the way, I realize we haven't talked about this symbol. This symbol right here means belongs to, or is an element of. Okay? So I'm saying, so let's read this together. A is an element of the domain of f. All together? A is an element of the domain of f. Okay? 3 symbols as opposed to a sentence. Okay? But if I take an hour to explain it, it doesn't really save any time. But we'll be using that symbol throughout this course. Okay? So if we've got either a polynomial function, remember those? Just powers of x times constants, and then you add them together. Okay? Or a rational function, that's one polynomial divided by another polynomial, then taking limits is not too exciting, provided the limiting value is in the domain of f. Okay? So what does this say? This says taking the limit is the same thing as, let me say that. Taking the limit gives the same result as simply plugging the number into the function. Okay? All right. I don't know how to emphasize this any more than to put warning and say it. But I see this all the time when people first learn limits. They get this direct substitution property and they think they can apply it everywhere. They think they can apply it in every single problem we do. And it's only if these conditions are met that you can do the direct substitution property. Okay? So students often assume the direct substitution property applies to all rational functions. If A is, what do you think this symbol means?
Not.
If A is not in the domain of f, then the property does, again, seems like a silly word, but I'm trying to emphasize it. The property does not hold. Okay? And other techniques must be used. All right. So I'd like to do questions 8 and 9, and I absolutely need you to understand the difference between questions 8 and 9 here. They are two completely different types of limit problems. In number 8, what type of function am I taking the limit of? What's the name of that category of function? It's a rational function, right? What's the domain of this rational function? The domain of, so if I say f of x is this rational function x squared minus 1 over x minus 1, then the domain of f is the set of x such that x is any real number except that x does not equal what? 1. Yeah, you can't plug a 1 into this function because if you did, you'd get a 0 in the denominator. Okay? That's one way to write the domain. Another way is to say it's minus infinity to 1 union 1 to infinity. Okay? So, let's just double check what we just did. We said, hey, we've got a rational function here, and the domain is everything except for 1. What is my limiting value? Nope. The answer might come out to be 1. Maybe that's what somebody was checking. When I say limiting value, I mean, what am I taking the limit of? As x approaches 0. Okay? Is 0 in the domain of this function?
Yes.
Then what do I get to apply?
The substitution property.
The direct substitution property. I can circumvent all those limit properties and just go straight to plugging in a 0 in this case. Okay? So this is just going to be 0 squared minus 1 over 0 minus 1, which comes out to be 1. Okay. Warning, warning, warning. Not all problems are like this. How many direct substitution problems do you think I'll put on your first exam?
1.
At most 1. Okay. All right. What's the difference between question 8 and question 9?
One isn't in the domain.
So everyone hear what Freddie said? The limiting value here, I don't know how that happened, is 1. Okay? The limiting value here is 1, and 1 is not in the domain of this function. So we're exploring how the function is behaving near a place where it's undefined. That's where, first of all, limits are far more useful than in question number 8. But it's also where the direct substitution property does not apply. Okay? So again, we've got this rational function. Again, the domain's all real numbers except for 1. But in this case, I'm taking the limit as x approaches that value 1. Okay? So how do I have to tackle this problem? By some other means. And this is actually similar to one I worked before. Okay? So I think did I say this in here that I bought stock in Dixon Ticonderoga? No, I didn't. That's a lie. I bought stock in Dixon Ticonderoga before the start of the semester, right? So the more pencil lead you guys use, the more pencils you use, the more new pencils you buy, the richer I become. I promise to split half my earnings with you at the end of the semester. Okay? For some reason, students don't like to keep writing this limit expression. You have to keep writing this limit expression. Use that pencil lead, make us rich. Okay? You have to keep writing this limit expression until you evaluate the limit by some means. Okay? I will mark you wrong if you don't keep writing this limit expression throughout the problem. Okay? Until you get ready to evaluate the limit. Because it's a subtle step. When did you choose to apply the direct substitution property? I need to know that you know exactly where you did that. And if you stop writing the limit right away, I don't know that you understand the problem. Okay, so the burden of proof's on you to show me that you understand limits. Okay? All right, so I'm working inside the limit, and I'm going to rewrite it as x, the expression inside the limit, as x minus 1 times x plus 1 all over x minus 1. Have I evaluated the limit yet? No, so I'm still writing the limit as x approaches 1. Okay? We saw this problem before. Notice that as long as x isn't 1, which it's not, because we're just approaching 1, we're not plugging in 1, I can cancel out those two factors. Okay? This gives me the limit as, so this is equivalent to the limit as x approaches 1 of x plus 1. What type of function is now inside the limit? You could call it linear. There's lots of names for it, I guess. Specifically, it's a type of polynomial function, right? Polynomial function, a linear function is a polynomial to the first degree. This is a polynomial function. What's its domain? All real numbers, right? So I can go ahead and evaluate this limit. How?
Plugging in.
Through direct substitution. Okay? So from this line to this line, I'm going to apply the direct substitution property. Which says that evaluating the limit of a polynomial or a rational function at a nice place is the same as just plugging in that number into the function, or gives the same result. That's a better way to say it. Okay. We can't quite see that, I'm sorry.
That's just the simple way of the direct substitution. You don't have to show that you're doing it any other way other than just dropping the limit.
Yep. So that's how I know. So that's why you have to keep writing the limit until you apply the direct substitution property, right? Because from this line to this line, I know what you did. You applied the direct substitution property. If you had stopped writing the limit beforehand, then I wouldn't know what's going on. Okay. Is there a question? Yep.
But you could use, instead of the direct substitution, you could still use like the product rule.
Very good.
Constant rule, right?
Yes, you could. So in this case, before you use either the product rule, the constant rule, any of the others, you would have to first use the quotient rule. Well, let me be a little careful here. You would try to use the quotient rule. But can I apply the quotient rule in this case? No, because there was a caveat. Remember I said there was that important caveat to the quotient rule? If you look back at it, we said you can, the limit of a quotient is the quotient of the limits provided the denominator limit doesn't evaluate to be 0, which it would in this case. So let me take that back. In a lot of cases, you could use all these limit properties to get all the way through it, like we did in the first example. You could not use limit properties on this one, because the first property you would need to apply is the quotient property, and we can't apply the quotient property because the limit of the denominator is 0. And that's actually...
You have to start it that way? Because if you do it starting from that point after you cross out the...
Oh, from here.
ones.
From here. I'm sorry, I misunderstood. Yes, you could do first some algebra, and then from here start applying your limit properties. Distribute the limit over the sum, and then apply both the limit of a constant as a constant and the limit of the identity. Yes, you could do that. Good. Yeah, so from here you can either use the direct substitution property or keep going with your standard properties and limits. Either way, you'll arrive at the same point. Great question. Yeah, and good observation. What else? Yes, Will.
So that problem seems fairly easy, but I don't think there's going to be like those.
Nope.
Would there be a problem where it will not cancel when you distribute?
Okay, so this is so question 9 is a very typical problem that we're going to ask in calculus for a lot of reasons. Okay, first of all, the place where I'm taking a limit is a place where the expression is undefined. Okay. Second of all, what we do is we hold off on evaluating the limit through direct substitution or some other means, and we start simplifying the expression inside here. Where these problems differ is how much work you have to do to cancel out the thing that was preventing you from using direct substitution to begin with. Okay? And sometimes the amount of work you'll have to do in those is quite intensive, and we'll look at one here in just a second. Okay? All right, so who wants to, I just want to make sure we get this point. So who wants to summarize what's going on between 8 and 9, the difference between question 8 and question 9?
Denominator is denominator in 8 isn't going to be 0, so you can use the domain for it, and then denominator in 9 it's going to be 0, or you can't divide by 0, so you have to use different means of going through the problem.
Okay, folks hear what Justin said? I was going to get there. So I had to look at the two names and rule one out. Okay, everyone hear what Justin said? Okay. That's on track. Yeah, I like that. Let's see if we can formalize that just a little bit more too. Another way of saying that? Another way of phrasing that? So let's just start off and say the big technique difference is we could not use the direct substitution property initially on question number 9. But we could use it initially on question number 8. For what reason? So Jordan said, hey, I look ahead and I won't get a 0 in the denominator. Justin says, I look ahead and I won't get a 0 in the denominator. Okay. The reason why we could say that is if we identified the domain of the function, the domain is everything except for 1, and we're taking the limit as x is approaching 0. So that's okay. Whereas here, we're taking the limit at a place where the rational function is undefined, so we cannot use the direct substitution property or the quotient property yet. But we could clean it up first by doing some algebra, and then either apply limit properties or the direct substitution property to finish it out. Okay, we're going to come back to these, but I want to, we missed a couple properties, so let's pick up here. So, we saw in this example, folks, in this example here, we were able to evaluate this product function. It was x times x. Okay? And the net result was we essentially just got the limit value squared. So we could summarize that as a property by saying that the limit as x approaches a of f of x raised to the nth power is equal to the limit as x approaches a of f of x, and then raise that whole thing to the nth power. Okay? Put another way, we could say that limits pass through the power functions. That's really nice. Okay, that's something you almost can never do in algebra. Okay. So we'll look at an example of that here in just a second. Okay. By the way, so the blank here is suppose that the limit exists. All of these properties that we're giving assume that the limit exists. If the limit doesn't exist, the underlying limit doesn't exist, then you cannot apply this property. Okay? So you might start by passing the limit through here and then find out that this limit does not exist, but that means that your previous step was an illegal step. Okay? We'll talk more about that as we go along. Okay? The next one is very similar. It says the limit as x approaches a of the nth root of f of x is the same thing as the nth root of the limit as x approaches a of f of x, meaning limits pass through the nth root function, okay, provided not only that the original underlying limit exists, but also that the particular nth root is defined. So it might be that this limit comes out to be a negative number, and if this were a square root, then I could not use this property. Okay? Well, there probably are questions. Let's put this into practice. Let's look at some examples. Okay, and then we'll check to see if there's questions. So let's go ahead and do B, again using these limit properties. Okay, so now I know I could use what? Because I kind of jumped ahead in the notes. What could I use in this case? Right? I could use the direct substitution property here. How come? Because I've got a rational function. Where's the rational function undefined? At, what is that? At 3/5. But my limiting value is -2. So I could apply direct substitution here, right? That means I'm going to go through all this work of using regular limit properties, and I'm not going to get a very exciting result. Okay? But I just want to practice these properties one more time. Okay? So the first property I need to apply here is the what property? I heard it, the quotient property, right? And what does the quotient property say? It says we can distribute a limit over a quotient with the one caveat. Whatever the limit of the denominator comes out to be, it cannot become 0. It cannot be 0. If it were 0, then applying the quotient property would be a mistake. Okay? All right. So let's apply that by distributing the limit to both the numerator and the denominator. See what I did there? By the way, I should put parentheses around this to emphasize that the limit is of that whole expression, not just the first term. Okay, anyone have any questions on that? Okay. That was by the quotient property. Then I can go ahead and use my sum and difference property to say that's the limit as x approaches -2 of x cubed plus the limit as x approaches -2 of 2x squared minus the limit as x approaches -2 of 1. Dragons. End of it. 1. All over the limit as x approaches -2 of 5x minus the limit as x approaches -2 of 3. Okay? This is tedious, right? I've already shown you the direct substitution property. Okay? So when the direct substitution, so careful, when it applies, you may go ahead and use it after this section. Okay? In this section in your My Math Lab homework, it will say identify which property you are using. Okay? And so you will have to do this step by step like I'm doing here. Okay? So in the numerator, I'm going to rewrite the first term as the limit as x approaches -2 of x all to the third power. Everyone see what I did there? That's by the property that I just gave you up above. Okay. That says limits pass through power functions. Okay. I could have also written this as a product, right? X cubed could also be written as x times x times x, but that would just take more writing. So there's often many ways, many routes to arrive at the answer if you're using limit properties. Okay? I need to see that a little better. All right, plus 2 times the limit as x approaches -2 of x squared minus a -2. All over 5 times the limit as x approaches -2 of x minus 3. Folks, for each term, I'm only ever applying one property at a time. Justin.
Why is it -2 at the end? It's the limit of 1.
Oh, that's a 1. Thank you, thank you. That's not an x.
Got confusing.
Yep. Good catch. Everyone see the mistake? I was thinking it was the identity function. It's a constant function.
Would it be +1 because it's minus?
Well, so remember, the limit of a constant is just the constant value.
Okay.
So it is this part, so the limit evaluated to 1, and then I just have the minus sign in front of it. So because this expression right here evaluates to just be 1, then it's just minus the 1. Okay, so there's two ways to, yeah, so no, you're quite right. So let's say I have the limit as x approaches -3 of x minus 1. Okay? So this is the limit as x approaches, in fact, let's do this. Let's do minus x minus 1. Okay? So that would be equal to the limit as x approaches -3 of minus x. And then here I have a choice. I could either write it this way, or I could write that second term as, well, let's write the whole line. The limit as x approaches -3 of minus x minus the limit as x approaches -3 of 1. Do you see that that's the same thing? Let's take a moment to think about that, folks. So I can either think about this as I'm subtracting the number 1, in which case I would use what was called the difference property of limits, which I didn't give you because it's really the same as the sum property. But it says, okay, I just distribute the limit over the difference. That's what I did here. Okay? Or I could think of it as a sum, in which case I'm adding to negative x the number -1, and here's the sum. So there's two ways of handling that. Does that clarify? Okay. Yeah, folks, always keep pushing on those questions if I don't do a good job answering it, because that's my fault. All right. So let's just finish this out. So this one would come out to be, eventually I would write minus a -3, but this one would just be -1. Because the limit of a constant is just the constant. But here, the limit of the identity, I actually plugged in the identity value for x. And then this negative was also floating there. Okay. All right. Great question. All right. So this gives me -2 cubed plus 2. And folks, I really should take one more line to pass this limit through the power function, but I don't really want to write this fraction one more time. Does everyone see what I'm saying there? So I should take one more line to pass this through the squared, but I'm just going to go ahead and do it now. Plus 2 times negative 2 squared minus 1 all over 5 times negative 2 minus 3, and you get a number. I don't know what it is. I'll just stop there. 1/13? Thank you. Ready? Do we have a consensus on that? Math by democracy, it's 1/13. Okay. Questions on that? So, if you look at the directions here, the directions of this problem, and this is why I think that it's important to, when you're working my math lab, always copy down the directions as well. Here the directions said, evaluate the limits by justifying each step, meaning you had to do it one property at a time. Okay? But going forward, you can use the direct substitution property where it applies, right? Okay. So, if you look, I think the only problem on here that I gave you where the direct substitution applies is question number 8. Okay? Everything else requires some work before you can get there. Okay? So I'd like you all to try number 10 in your groups. Okay, give this one a shot. Okay, if you get done with number 10, go ahead and jump into number 11. Give that one a shot.
So pretty much I applied the limit to this entire thing. Well, first I had to like steal it. And when I did that, I got this. X squared plus 6x over x. That's a tiny function.
Go ahead and try number
There I cancel the x. We cancel the bottom one, the top one down. The function I got was x plus 6.
So,
This is what I got after.
here's how this problem is similar to the last one.
This one has
First of all, I can't apply the direct substitution property. Everyone see that? I can't apply the direct substitution property because 0 is not the domain of that function. And that's where I make the limit. So the trick is to try to rearrange what I've got inside of the limit and maybe be able to cancel something else. I agree. I agree. You can apply the quotient property either because the limit of the denominator is 0. So let's clean up the numerator. Let's go ahead and expand that out and see what happens. Boil out that numerator and cancel some terms and see if we can do anything there.
But you're right, that works out.
Folks, how we doing here?
It's mixed.
So let's be a little careful here. You're starting to apply limit properties. The first one you would apply would be the quotient property. Can we apply the quotient property here? So the quotient property comes with a caveat, and it's provided the limit of the denominator expression doesn't turn out to be 0. If you look ahead, when you distribute that limit to the denominator, you get 0. So you can't apply limit properties yet. So this is more like question number 9 up here, and you're going to have to do some cleaning up of the function first. So go ahead and just keep writing the limit there and clean this up somehow. So I would recommend foiling that out. Yeah. So no, because why? Because you've applied the quotient property.
You have to take an x
You can't
out, so
apply the
x
quotient property.
times
Why not? The limit of the
Yeah,
denominator
six
turns out to be 0, and that's the caveat to the quotient property, right? All right, folks. I'm seeing a few issues here that I want to address right away. Okay. This problem number 10 is more like question 9 than any of the previous questions we've looked at. Can I use my quotient property on this problem?
No.
How come?
You get a 0.
Because the limit of the denominator would come out to be 0. So can I just go ahead and start distributing this limit places? No. Okay. In fact, one way to look at this is a rational function. Okay? And it's undefined at 0. And that's precisely where we're taking the limit at. So instead, if you go back to our warning, right, it says essentially you're going to have to rearrange the limit somehow. Okay? So instead, let's go ahead and just work inside of this limit, cleaning it up some. Okay? What could I do? Somebody give me a suggestion. Yeah, we could foil it, unfold it, foil it out, expand it. Okay? If we do so, we would get 9 plus 6x plus x squared minus 9 over x. Okay? Now, what could I do next? I heard it.
The 9s cancel each other out.
Did everyone see that? So the 9s cancel each other out. Now that may or may not be helpful. In this case, I think it's really helpful. I'm going to rewrite the problem here. You don't have to rewrite it, but I'd like to. Now, what could I do?
Factor out the x.
Yeah, I could factor out an x now, right? Okay. So this gives me the limit as x approaches 0 of x times 6 plus x all over x. Okay. Desiree, what would you like to do next?
Cancel out the x.
What's that? Okay. Yeah, so we're getting caught up here. So I still can't. Can I apply the limit properties yet? I still can't. I still can't apply that quotient property. Why? Because this pesky factor of x here. But what could I do? I can cancel those x's out. Exactly. Okay. So this gives me the limit as x approaches 0 of 6 plus x. And now, what have I got? A nice polynomial function. I can now evaluate this through direct substitution, and we just get 6 plus 0, which equals 6. Folks, how long did you write the limit for? Look at your work. Okay? I'll bet about, well, I've emphasized it. I'll bet about 25% of you stopped writing the limit as you did your work. Will you get full credit on the problem? No. No. You'll get -2 out of a 5-point problem if you don't write that limit all the way through. Okay? I'm just trying to get rich. I want you guys to waste as much pencil lead as possible. Okay? Questions on that? Yeah, Mike.
Just an admin thing. Am I going to get dinged if I skip the little one where you crossed out the x?
No.
Just went straight up?
Nope. Nope. So that's where, I mean, you're doing canceling in your head, you're doing factor formula, things like that I'm okay with. Okay? I don't think you can go from here to here. If you go from here to here, I know definitely that you just plugged in tiny numbers in your calculator. And then said, oh, I got an answer of 5.99999. I'll bet the answer's 6. Okay? But you're missing the entire, the whole business of limits if you do that. Okay? And I need to be able to recognize, like I said, I need to see exactly where you were then able to apply the direct substitution property. Okay? Let's do another one. All right, folks, does this one look familiar? Say sure.
Sure.
So this one I gave you in section 2.2 when I gave an example of where a computer will give you the wrong answer if you zoom in too far. Okay, remember what the answer was this? It was supposed to be 1/6. Right, but we zoomed in too far and the computer started giving us that round off error. Either the graph looked outrageously erratic or the Excel gave us 0. Okay. Let's see if we can get the correct answer. Let's see if we can outsmart the computer here. Okay. All right. I've told people that in calculus it's where you get good at algebra. Okay, because now it's algebra with a purpose. Okay. So there was a technique you learned in Algebra 2 called rationalizing the denominator. And put another way, in that technique what you did was you multiplied both the numerator and the denominator of an expression by the conjugate of a square root expression. Okay? You didn't know why you were learning that skill, because it really didn't have a point. I mean, that whole, you shouldn't have radicals in your denominators is like your grandma's math rule. Okay? It's like you can't end a sentence in a preposition, right? Everyone does anyway. Right? Okay. So we're going to be using a lot of those techniques from algebra that you said, why am I learning this? Well, this is why, for these types of problems right here. Okay? So let's just talk through this a little bit. Okay? Can I use direct substitution on this problem?
No.
No. Can I use the quotient property of limits? No, because the limit of the denominator is 0. Okay? So I'm going to have to do some rearranging of this. Eventually, I would like to somehow cancel out that x squared factor. That's what I'd like to eventually happen. If I'm going to be able to evaluate this limit, I'm going to hopefully be able to cancel out that x squared factor. Let's see what we can do. Okay? So the trick here, when you have an expression that has a sum or difference involving a square root, is to multiply the numerator and the denominator by the conjugate of that expression. Okay? So we're going to take the limit as x approaches 0 of the square root of x squared plus 9 minus 3 over x squared, and I'm going to multiply to that the square root of x squared plus 9 plus 3 all over the square root of x squared plus 9 plus 3. All of that is happening inside the limit. Okay. So again, for a binomial like this, the conjugate of a binomial is the same two terms, but with an opposite middle sign. That's what I mean by conjugate. Okay. All right, folks, I have multiplied these out 1,000,000 times. I wish you had as well. You're supposed to have. It's a prerequisite for this course. Okay. Normally when I multiply these two terms out, I will do them in my head, and I'll just write it out. Okay. Today, for the first time through, I'll go ahead and write it on the board for you. Okay. So the square root of x squared plus 9 minus 3 times the square root of x squared plus 9 plus 3. Let's go ahead and FOIL this out. Okay? So foiling says you take each term in this binomial times each term in this binomial. So let's do our first. I multiply the square root times the square root, right? So that would be the square root of x squared plus 9 times itself, so that's the same thing as it squared, which will get rid of the square root. Then I'll do my, I think we called it the outers. Okay, so that's plus 3 square root of x squared plus 9. And then minus 3 square root of x squared plus 9. Oh, look at that. What happened to my outers and inners? They canceled. Is that a coincidence? No. That's why we multiplied by the conjugate. Multiplying by the conjugate forces the outers and inners to cancel out. Okay. Then we do our last, and we get minus 9. Okay. So let's clean it up. When the smoke clears, we've got x squared plus 9, outers and inners cancel, minus 9. Folks, I will usually just write this in the next line. Okay? That's why? Because if I write this out, I make a mistake. I do better to just jump to it. Okay? You are welcome to either get really comfortable with this and do it in one line or do it in 2 lines. That's up to you. Okay? So, at a certain point in this class, you're going to say, what did he do? Okay, now let me do that. Rather than saying, I completely understand from this line to this line. Does that make sense? Meaning that you're going to say, oh, I know how to do that as well. I'm going to assume that if I did it, I'd get the same answer as him, and maybe I'll come back and check that in a moment. Okay, that's just kind of how that's just how math works. Everyone does problems their own way. When you're reading a math book, you'll say, oh, they're multiplying by the conjugate. I've done that before. Let me go off to the side and work that on my own. Yep, I got the same answer as the author. They're not going to show you every step along the way. Okay? All right. So cleaning this up, we get the limit as x approaches 0 of, what do we say, x squared plus 9 minus 9 all over x squared times the square root of x squared plus 9 plus 3. How we doing? Okay. You looking down the road a little way? Looking down the road a little ways, getting a good feeling about this? Let's not get lost. we wished we could use the direct substitution property, right? But we couldn't because of that x squared term in the denominator, right? We're getting closer to being able to cancel that out. Okay? This cleans up to be the limit as x approaches 0 of just x squared over x squared square root x squared plus 9 plus 3. Now the x squared terms cancel, right? I'm going to write this one more step just so you see it. The limit as x approaches 0 of 1 over the square root of x squared plus 9 plus 3. Okay? All right. Technically here I'm not using the direct substitution property. Technically here what I'm going to do is distribute the limit over the quotient and then distribute the limit in the denominator to each of these two terms, and then what? Pass the limit through the square root. Can I pass a limit through the square root? That was one of the properties that I gave you on the previous page. Okay. I'm just going to go ahead and jump to it though because it gives you the same result. So this is 1 over 0 squared plus 9 square rooted plus 3, which is equal to 1 over the square root of 9 plus 3, which is equal to 1 over 3 plus 3, or 1/6, as we suspected. From the, remember we looked at it in Excel, and it was getting closer and closer to 1/6, but then when we zoomed in too far, it started jumping around.
So at this point you did do direct substitution.
Yes. But
Because you can add the 0 into the x squared and it won't make the whole denominator 0, which is why you could use it, right?
correct, correct. That's exactly right. So now notice my denominator limit did not come out to give, the denominator didn't come out to be a 0. Okay, so I could go ahead and use, it's not quite the same direct substitution property I gave you because it has a square root in it, but yeah, let's just leave it there. Whew. Folks, algebra just showed up and it's not going away for the rest of the course. Okay? All right. These are tough, and when I write the test and when I give you time to do the test, I assume that you look at this problem and say, aha, my first step is to do this, and you get going working through it. Okay? If you look at this problem and you kind of fiddle around with it for a while, you're going to slowly run out of time on your test. Okay? I would recommend putting a problem like this on a flashcard, and on the back side not solving it, but just say, what is your first step? Right? Write this type of problem on a flashcard. On the back side, write multiply by the conjugate over itself. That's your first step. Okay? Because I'm going to show you different tricks for different problems. Yes?
Just admin question. Are we allowed flashcards or
Not on a test, no. On the final exam, you're allowed one 3x5 card, but not on the exams. No. Okay. Great. Holy smokes. All right, let's keep rolling. All of the above properties extend to left and right hand limits, and now we're going to explore one of my favorite questions in the class. This question will show up on your first exam. It'll show up, some version of it. It won't be exactly the same. Some version of this question shows up on your first exam. It'll show up on your final exam. Okay? If I had my druthers, it'd be a pearly gates question. No. Anyway, let's go ahead and look at the limit of the absolute value function as we approach 0. But we're going to have to use left and right hand limits here. Okay? So first of all, what does the graph of the absolute value function look like? Yeah, the graph of the absolute value function is a V. Okay? For positive x values, it behaves like the identity function. Plug in 3, it spits out 3. Plug in 12, it spits out 12. For negative x values, it behaves like the reciprocal of the identity function. Plug in negative 3, it spits out positive 3. plug in negative 12, it spits out positive 12. Okay? Let's take a guess. What do you think the limit should be? Oh, in fact, I tell you here. I tell you to show that the limit is 0, right? And you can see that from the graph, right? It appears to me that as we approach 0 from one direction, the y values are approaching 0. And as we approach 0 from the other direction, the y values are approaching 0. Okay? So,
We should just be able to write that on the test.
I
Nope.
was just
nope. Nope.
So close.
It's not too bad, though. What I want to remind you, though, is that the absolute value function is a two-part definition function, and I just tried to show you that by way of the graph. Okay? So remember that if I define the absolute value of x is defined to be just x if x is greater than or equal to 0, and it's minus x if x is less than 0. And you can see that by way of the graph, or think of how you take an absolute value. It says if the number is positive, leave it alone. If the number is negative, change the sign on it. So, remember we said before that one way to show that the limit is a number is to find the left-hand limit, evaluate it, find the right-hand limit, and evaluate it. Okay? I cannot use the direct substitution property on this because it's not a polynomial or rational function, which is why we have to do it this way. Okay? So, step one, let's look at the right-hand limit. Of the absolute value function. So which way am I approaching 0? From the right. I'm coming in from this direction. So normally if I say come towards 0, you don't know which one of the two rules you're supposed to be using, right? Because I say you have to be coming from the right, which of the two rules are we using? Will?
Oh, just the identity function.
Just the x function, right? Does everyone see that? Okay? So we're coming in from this direction, so we get to just replace the absolute value with x, only because we've specified the direction of approach. Okay? But this was not a polynomial function. This is an absolute value function, right? This is a polynomial function. So what do we get to use? The direct substitution property. So that's just equal to 0. Yes,
If you
Sean.
go right, are these notes that you have like everything filled out? Are they going to be uploaded?
What I'm doing right now is I'm uploading the video of these notes.
Okay.
So you might have to sit there and watch it.
Okay.
I don't know. I'm not a very organized person, so remembering at the end of class to save this document and not get it confused with the document I use in here with my next class is too hard.
Okay.
So
I was just going to ask if you could, like, just on the little side, if you could write like applied direct substitution or like shorten it to like.
sure, yeah.
PDF.
Let's do that. I like that. Like so, right here between these two steps, let's see, applied direct substitution. How's that? Between these two steps, we apply direct substitution. I like that. Okay. All right. So now that was the right-hand limit. What should we do next? Let's take the left-hand limit of the absolute value of x. Okay. I don't have a property that allows me to pass, this is very important, folks. I don't have a property that allows me to pass a limit through an absolute value. Okay. So I'm having to use some other means. In this case, I'm returning to the definition of the function. Since I've specified the direction of approach, I get to use this particular definition for the absolute value function. Okay? This is equal to the limit as x approaches 0 from the left of what? Of minus x. Okay? Folks, where did the absolute value go? Did I wish it away? Did I say, oh, I wish it wasn't there? Did I say, oh, I'll make numbers positive at the end? No. What did I do? I went to the particular definition component. and applied that. Okay? If you ever say, I'm wishing away an absolute value, you're wrong. Okay? Yes?
So if the absolute value graph was like shifted to the right, like 3, would you have to shift, or would you have to like add or subtract 3?
So if I were asking, let's say this, let me just say, if I were doing the limit as x approaches 3 of the absolute value of x, you could make an argument to say that as you get close enough to 3, regardless of the direction of approach, your x values are positive. And so then you could say that's the limit as x approaches 3 of just x. But there's a little bit of a talking point that happened in between there. And then you could say that it's just 3. If I shifted the curve, if I were looking at this, absolute value of x minus 3, okay, then again, this is a critical area that you need to explore carefully, right? Because whether or not the expression inside the absolute value is positive or negative depends on the direction of approach. And we're going to look at that down below here. Yeah. So anyway, we can now apply what here? Direct substitution. So we get -0, which is 0. What have we just shown? Yeah, so we just showed the right-hand limit is 0 and the left-hand limit is 0. So the limit as x approaches 0 of the absolute value of x proper is also 0 because the left and right-hand limits exist and they agree.
We're gonna have to do this for all the problems going forward, right?
If there's an absolute value with it, you typically have to break it into, unless it's a boring problem, if there's an absolute value, you have to break it into left and right-hand limits. If I ask you, generally on a test, I'll say, evaluate this limit. You need to be doing some sort of algebraic work to do so. Okay? You can't plug in numbers. Yeah. So right now, it's like, so I guess is what I've said is that, let's look at something a little more typical.
Like, are we gonna have to memorize all the different functions and then be able to prove it based on the shape of it and doing the 2-part?
So notice, I would have the absolute value function memorized. Notice that I never actually used the graph. I used this definition right here. The graph sort of guided me, but yeah. So in this class, I will be calling upon your knowledge of all of the standard functions, which includes absolute value function, basic polynomial power functions, your trigonometric functions, and E and natural log. So I'm working you into it, but yes, yeah. Michael.
As far as like the definition when we do the thing on the test, do you want us to write the absolute value of x equals that piecewise function and then solve it, or that's just like something that we just know and then we just solve it?
I would recommend writing this. Again, the only thing you're out is a little bit of pencil lead, and I'm splitting the profits with you anyway, so you get your money back. Okay? And so I would write it out, but no. But you do have to show me these 2 steps. And I don't think you would know these 2 steps unless you had this definition memorized. Okay? All right. So, running out of time. I'm going to change this problem on you folks. Let's do this as the limit as x approaches 3 of the absolute value of x minus 3 all over x minus 3. Okay? It's the exact same problem. It's just shifted over. Okay? And this is more typical of what you'll see as a test question. So here I've said prove that the limit doesn't exist. Okay? How would we maybe show that the limit doesn't exist? What's one way to do it? I can't. We can't do the graph. If I showed you the graph, I guess you could go with it. But generally, I want something more than that. Really?
Direct substitution?
So notice here, if we did direct substitution, we would end up with the expression maybe 0 over 0. And in math, 0 over 0 is not anything. It might, so 0 over 0 is not something we can ever write as an expression. So another way of saying that is we can't do direct substitution because the limit of the denominator would be 0. Yeah. So that's a good guess. Michael?
So you're just gonna like split it up and show how the limit approaches x of 3 from the left?
So we'll find the limit from the left, we'll find the limit from the right, and if we're going to show these do not exist, what do we expect?
Zero.
We expect them not to agree with each other. Okay? The left-hand limit and right-hand limit aren't the same. Yeah.
Or just do not exist.
Yep. So if one of them doesn't exist also. So if the left-hand limit didn't exist, then neither would the limit proper. Yeah, it's true. Okay, so let's go ahead and look at the left-hand limit. Okay. So, in fact, what's preventing us from doing this direct substitution here? That x minus 3 factor in the denominator, right? We would like to cancel that out somehow. We'd like to have a way to cancel that out. Okay. Can I just wish away the absolute values and then cancel them? No. I wish. Okay. But let's reason this. Let's reason our way through this. We're approaching 3 from which way? The left. So I'm going to be plugging in numbers like what for x? Not negative. Like 2.9, right? Or 2, 2.5, 2.9, 2.99. What happens when I subtract 3 from those numbers? I always get something that's but what sign? Small but negative, right? I always would get something that would be negative here, right? So by the definition of absolute value, okay, in fact, let's write that up here. The absolute value of x minus 3 is just equal to x minus 3 if the expression is positive. Let me put this down here. So the absolute value of x minus 3, because this is something I think a lot of people are missing from absolute values. It's just equal to x minus 3 if x minus 3 is what? Greater than or equal to 0. Put another way, if x is greater than or equal to 3, I can just leave the expression alone. Okay? But what if x minus 3 is less than 0? That is, what if x is less than 3? What would I do? This part's really important, folks. What do you do with the number inside of an absolute value if that number is negative? You change the sign on it. What's inside the absolute value? Not x. X minus 3 is inside the absolute value. So you change the sign on it. All of it. This is what a lot of people are missing about an understanding of absolute value, and that's because somebody once a long time ago said, hey, just make numbers positive when you see it. It is more subtle than that. Okay? Okay. Which way are we approaching 3? From the left, meaning this expression inside the absolute value is always negative. So what do I do to it? I change the sign on it. Did I wish away the absolute value? No, I applied one of the two definitions to it because I specified a direction of approach. Okay? Will, I'll get to your question here in just a second. I can cancel these out now, these two factors. What am I left with? The limit as x approaches, the limit as x approaches 3 from the left of -1, but that I'm taking the limit of a what?
Constant.
Taking the limit of a constant. What is the limit of a constant? It's just the constant. So I just showed that the left-hand limit for this function is -1. Let's repeat it for the right-hand limit. Okay. I start off with the absolute value. That's where we started. Okay. Now I'm always plugging in numbers like what for x? 0.4 or 3.5 or 3.1 or 3.001. Regardless, when I do this difference, I always get a small but what number? Positive. The expression inside the absolute value is always positive. What do we do with an absolute value when the expression is positive? Leave it alone. Right? So this is equal to the limit as x approaches 3 from the right of x minus 3 over x minus 3. Which is equal to the limit as x approaches 3 from the right of 1. What is the limit of a constant? Just the constant value. So this limit is 1. What was that?
Negative 1 and 1 does not exist.
Yeah, so we just showed the left-hand limit was negative 1. The right-hand limit was positive 1. So the limit proper does not exist. Okay. By the way, if you were to graph these two functions, the graph of these two functions looks like this. No, it doesn't. It's a lie. The graph of these two functions looks like this. There's negative 1 and there's 1. What do we see? As we approached 0 from the right, the limit was 1. As we approached 0 from the left, the limit was negative 1. So I asked somebody, how could we do this? You said, look at the graph. Well, yeah, the graph demonstrates that the limit does not exist. Okay? But again, just looking at a picture, we have said, isn't good enough. Okay?
Is that shifted over, or is that just the
Oh, shoot. Yeah. Thank you. Let me fix that. I went back to how I originally wrote it.
Oh, yeah.
There we go. Who said to move it over? Great, thank you. Justin. We started out all touchy-feely. Limits, getting close, what's it like? Okay. I think it probably just got a little bit harder today. Okay. Folks, this is not the time to say I'm going to go home and master this by myself. Okay? This is the time to say I'll go home, review my notes, but then as soon as I can, I'm going to get some help, either by going to the math center, by coming into office hours, by forming a study group. Okay? Now is the time where you can't say this is just going to start making more sense the next time I come to class. Okay? Because it's not. You got to start figuring it out now. Okay? Yeah, Sean.
Is this, what kind of questions should we expect on the next quiz? Are you able to do this thing?
Yeah, I'm a little overwhelmed.
What do we need
right?
to master?
I'm not going to, let me say this. It'll either be the square root one, the one where the answer was 1/6, one like that,
Okay.
or one like this. Yeah. Okay. All right, folks, that's all I've got for you today. We're about a section behind. I'm not scared yet. Okay? We'll keep working at it. Okay? If I need to postpone section 2.6 until after the first exam, we'll do so. Okay? But please go ahead and start working on the math lab for 2.3. You should be able to get through it now. Okay? That's all I've got. Have a great day. Yeah. Yeah, great. No, so this simplifies. What about direct substitution here? What did you rewrite this as? You can rewrite it as 1. So first of all, let me just say, this work is 100% correct. That's good.
You need me.
But what is x divided by x?
You need to use me.
So first you would write the limit is x equals to 0 divided by 1.
No, dude.
But then that's just
No,
so
dude.
the answer is 1.
It's over. It's over.
So this part is wrong and
Like in my class? No, I'm here.
exactly.
I'm in this class.
Great, great, good. Yeah.
Yeah, I'm in it. Well, I'm not there. We just started.
Yeah, so that has to do with, yeah, that's a great question.
You had two
So
classes.
a conjugate,
All just started. That's a different
the conjugate of a binomial is just the same expressions on each side of the sign with a different sign in the middle. Okay? So that A could be anything. It could be the square root of x plus 2 as conjugate
That's a no.
square root of x minus 2. Right? It could be the square root of x plus h plus 2, but it has conjugate, so this is an important skill, right? Looking at this complicated thing, the first thing I see is two parts. I see this part and this part are solid.
I usually said
So this is called a binomial.
I woke up at 9:15. So I was
Take
like,
the conjugate of a binomial, you leave the two terms alone and change the sign in the middle. Okay, so in fact, let's put a minus sign here. So it has a conjugate, square root of x plus h. There's the first term.
I left my
There's the
house
second
at
term.
9:15.
And what do I do with the sign between them? Change it.
115 in Colorado. So 115 in Colorado.
Yeah, so it's whatever's separating the two.
I go down to 112.
Yeah, thanks for asking. Derek?
Yeah.
Dalton, I'm sorry.
Still a D.
Like kids over here, lovely kids, texted me, she's like, hey, I'm gonna be late for class.
Because that's like.
I was able to tell
That's
BT
like a
here,
good spot for me.
hey,
Send-
Like
Caleb's gonna be late
testing
for
and
class.
stuff like that.
One thing you can do is, I don't have like a,
And then he got commended for telling me.
review exercise. Send me an email, I can send you a document that
So
has,
you should just,
that lets you fill in the unit circle and then you can answer a bunch of questions from it. And then I can get that, and you can try what you can in your own and talk through it.
Okay.
I will do a little bit of a unit circle review when we get to.
I not know.
So first of all,
I will
there's
take a
no
short pass on that.
When we get to
No, I'm good.
section 3.5, we're gonna do something very special with the functions. So
Sean.
at that point, I'll do a little bit more of a
with an
formal
S, is
review.
there another
But I
way?
think the highest one is.
You can spell it
Well,
Sean.
it already, I already started showing up
Yep,
with the homework, and I was
yep.
like, oh my god.
Yep.
I don't have any of my stuff from pre-cal.
And if you come by, I can show you some tricks that I have,
Okay.
for doing so, but I haven't put those into a
Okay,
video.
I'll see y'all later.
Hey, buddy.
Yeah.
Okay.
Okay, great, thanks,
Hey,
Andrew.
Sean, if you need
Justin,
help with
I-
John,
The only
just
reason I
text
really
me.
pointed it out.
Yes,
Do you
for
have a
sure.
tip for remembering how which way you slide over? Because I always forget that -3 in these cases you have
I
to
do.
switch over to the right.
I do have a way to remember that.
Like I know it's probably as simple as long as you actually get it in your memory. It's just I always forget.
No,
that
but I
-3.
think, I think anything you do in math, you should be able to kind of rationalize your way through as well. Okay? So let me just show you this. If I give you this function here, the square root of x, what's its domain? Just x. And 0,
I'm gonna go get
right?
lunch now.
Okay. So why? Because you can't take the square root of a negative number.
Okay.
But,
If I put f of x is equal to the square root of x minus 3, what numbers can I plug in here?
Oh, okay. Because the domain is only still positive. It has to
come
be
to class and just
3.
your phone.
And so what happened to the domain?
You just shifted it.
It got shifted which way? To the right. What if I looked at f of x is equal to the square root of x plus 3? I can now plug in a few negative numbers, like -1 for x, right?
So you're just shifting the domain over.
Yeah, so the,
Would
dom-
it just
so
be
the domain is,
-3 comma infinity?
You did the
Exactly.
same thing
Or
in,
or
I guess
not
pre-calculus.
actual. I thought it
Does
was
it though?
infinity minus 2.
What do you get out of this?
I mean,
so what happened to the domain? It got shifted which
sure.
way? To the left. So I put a plus sign, it shifted to the left. I put a minus sign, it shifted to the right.
We had a video camera.
so that's just because you can plug in, you can still plug in like 2.99 for x, and you'll get 0.01 as positive numbers. You can still use So would it be
Do you?
like? Oh, I always
What's his
forget
name?
the parentheses and I always
Bracket
forget-
means that it's included.
Oh,
So
yeah.
I can plug in a 3. Because what's 3 minus 3? 0. What's the square root of 0? 0. It is defined. So as opposed to f of x equals the natural log of x, its domain is 0 to infinity, because you
I
cannot
didn't,
take the
I
natural
didn't
log
study.
of 0.
Okay.
Like a single time.
Then the only other thing is just the
I don't
piecewise
really
function.
study.
I don't know if that's what it's called.
Mhm.
Oh,
The absolute
I don't have
you
to
get
study,
like the
which I've
positive
never
and
had to
negative
study.
part.
Yeah, so the absolute value is a
That's why
type of
I
piecewise
studied.
function.
Yeah, it's just that like
Because I've
the
never studied.
bracket thing that you explain over there. Like if x is this, that I understand those for the simple terms, but for the more complex terms, that's when I'm going to start getting confused. Because that was what that was what tripped me up a lot in first time I took calc. Was either that or the shifting stuff.
So one way to look at it is, I mean,
makes sense.
you always return to the stuff
all of it?
inside the absolute value. If the stuff is positive, you leave it alone.
Okay.
Okay, if this is the stuff that's inside there, if it's positive, you leave it alone.
Okay.
But then you could solve this inequality, right? How would you solve this inequality for x? You would add 3 over to the other side.
Okay.
So another way of saying it is if x is greater or equal to 3, then the stuff inside the absolute value will always be positive, in which case you leave it alone.
She's from Greece.
Yeah.
Yeah,
Good.
she said that.
Did that help?
Yeah, I just,
You guys
the one thing that did confuse me there is the greater than 0 and greater than equal to 3.
Well,
I forgot
she
why
said that.
The stuff
both.
inside has to be
Some
greater
reason
than
I
equal to
knew that.
0,
Oh, no.
and the stuff inside will be greater than equal to 0 if x is greater than equal to 3.
Cheating.
Oh.
Like I said, just solve this inequality.
Okay.
By isolating x, what would you do? You would add 3 over, and then that's what you would end up
They're
with.
both different?
No.
Okay. So it's just missing the if statement
Yeah,
there. Well, it's not really
more.
missing, it's just included, but,
More
okay.
efficient.
That makes
Yeah,
sense.
so normally I would actually just write this. Just write x minus 3 if x is greater than or equal to 0.
Okay.
Or excuse me, if x is greater x minus 3 if
Greater
x
than
is greater than or equal to 3, but this is the work that justifies
Makes sense.
why I
Okay.
picked that number.
Okay.
Yeah, yeah. Will?
Is this calculator can?
Speaking of which, let me make sure mine is okay. I thought I'd get one that works for everything.
So,
I try to find the TX that what is it? 30.
36.
yeah,
I
the
have-
36,
I have
well,
that one.
36 is okay, but this 36X Pro, so we have not officially banned this calculator in our math department.
But you're
But
going
we're
to.
trying to, those of us that are, I don't think we should use calculator
I
at
don't know
all.
how to use the other.
Hey,
That's fine,
Except what
but
I need that.
how, so anyway, here's what, so the reason why I want to ban this and say, no, you can't use it is because if you use these terms, you will get answers without having to do the work for them. So my workaround to that is just say you have to show me the work. Okay. So you can use this, but you have,
Do it to
then
prove
you
your
have to be
answer.
doing more, you're gonna have to be doing more paying attention to class and saying, what work do I need to show?
Do it to prove your answer, not get your answer.
Check your answer, yeah.
But I'm assuming the same thing for
Because
mine. It's
you said that
FX
at the end of the
9750.
second test we have to be using our heads instead of calculating things.
Mm-hmm.
So
Yeah, so
I don't know how that will.
So I won't, so if you use this on the, I'm not gonna say you can't use this on the test, because you bought it and you got it, but you'll just have to be paying attention, and as you learn how to use some of these more complicated things in here, make sure that you're still showing me the work that goes with it.
What if I buy the other ones instead?
Then you'll be, then you're in much better shape.
I mean, I think the only issue is for us is that
Yes.
we have
This is-
intro
I'd
chemistry
highly
as well.
recommend.
Yes,
one.
this is the one, actually, this isn't the one I recommended.
We have
Good.
intro
It's just
chemistry as
statement.
well, so
Yeah.
I think they
Good.
suggested a calculator that had like all the scientific notations and all that
Uh-huh.
stuff for for
Yeah,
chem
so
as well. So
yours-
those kind of compromise between.
No, yours is fine.
Which.
Oh,
ones
wait,
you
this
do.
is with this graphs.
Yeah.
I can't let you have this. So
Okay.
we do specifically say no graphing calculators.
Okay.
You're welcome to use it for homework and such, but I'd recommend getting, I posted that handout that has some calculators on it between 13 and 20 bucks,
Okay.
which I know isn't nice to have to spend, especially when you already got one. But
Good thing about
yeah.
this one, if you have Costco, you can get 2 for like $12.
okay, yeah.
And then you can just split it with
In
something
fact,
else.
is this the one I just recently recommended?
I don't know which ones you recommended, so I don't know.
That's all right.
I
This
already-
one actually might be so. Yeah. So
I got this one. Rita really liked that one.
yes. So I went off of Rita's. So I included the one that Rita mentioned.
Okay. I think
Uh,
she mentioned it. Maybe did she just mention it recently?
Yes.
She probably mentioned it because I had it in her class.
Okay. Yeah, that very well might be it. 'Cause-
Yeah.
yeah.
You know how this in her class too.
Okay. Well, so again, I'm not forbidding this one. It's not a graphing calculator, but it does. You have to know that it.
Something I'll do.
Okay.
when you have me to
So,
prove.
for example, we're gonna learn how to take a definite integral,
Yeah.
And now it doesn't.
and this is going to do all the work that I'm going to teach you how to do
And one question.
in one step. Well, if you write this equals this, I can't give you points for that. Because there's a lot of work that goes on to show this. So it's
Okay,
just knowing that
makes
you
sense.
can't use this function, you can't use, so these blue ones, can't use this one, can't use this one. These polynomial solved, can't use that. If you use them, you also still have to come back and show your work for it. Show work for it.
I'm gonna go the other one because I get into tape.
Okay, okay.
I will
I
see you
understand.
in 6-ish hours.
Okay, sounds good.
I understand the requirements for it. I'm just sitting here, I'm like, I don't even know how to use the graph on this thing. It's
I
very,
know.
it's
But
very
we have to, I mean, but some
Yeah.
people would, and, you know, and I can't say,
Yeah.
I can't say you can use this calculator provided you don't press this button, because I can't enforce that.
What if I just go through and change the code on it, you know? Me and him can team up and change the code on it and not graph anymore.
No, I'm getting my ass.
Delete the graph.
I tried to drop you off, but I have something to do.
Oh, okay, that's all right, yeah. When it works,
I'm trying to, he and I are trying to make this.
good. I do recommend doing that. I'll try.
I was needing a third person.
We tried to get Angel as well the first day. We saw her in the hallway. We tried to get her as well. She hasn't responded to any of our.
Okay.
I tried to see if she was doing okay, and Cal, after she asked a whole bunch of questions last week, or 2 weeks ago, whatever it was.
Yeah.
And she never responded. He tried to see if she still wanted to join that study group, never responded. I'm like, all right.
That's all right, yeah, that sometimes happens. But yeah, maybe ask some other folks, yeah. I'm sure you'll find somebody else that's interested.
I mean, depending on how long the study sessions are, we could do it between this class and chemistry. We have like 2 hours.
What chemistry do you have?
Chemistry 101 is 1:30 to 4.
Just the intro.
Oh, I'm still recording, Doug.
Who do you have?